September 5th, 1977, Cape Canaveral, Florida. A Titan III rocket lifts off carrying a spacecraft the size of a small car. Its name is Voyager 1. Nobody at the launch pad that morning knows it will still be flying and still talking to Earth nearly 50 years later. Nobody knows it will one day go silent for 5 months and come back from the edge of total loss. The mission plan calls for 4 years. The spacecraft has other plans. The rocket itself is not a new design. It is a Titan IIIe built from components with roots in Cold War missile programs, paired with a Centaur upper stage burning liquid hydrogen and liquid oxygen. 16 days earlier, its twin, Voyager 2, had already launched on a slower, longer path toward the outer planets. Voyager 1 launches second, but on a faster trajectory, one designed to let it overtake its twin and reach Jupiter first. By the time both spacecraft clear Earth's gravity, they are moving at speeds few human-built objects had ever achieved on courses calculated years earlier, when the outer planets aligned in a way that happens only once every 175 years. A rare geometric gift that lets a single spacecraft use the gravity of one planet to fling itself toward the next. Voyager 1 carries 11 scientific instruments, 3 cameras among them, and a power source built to outlast its own timeline. That power source is a set of 3 radioisotope thermoelectric generators, devices that turn the heat of decaying plutonium-238 into electricity through nothing more complicated than a temperature difference and a stack of thermocouples. There are no moving parts, no fuel to refill, no way to service them once the spacecraft leaves Earth. At launch, they produce about 470 watts, barely enough to run a couple of household appliances, and every watt has to be rationed between instruments, transmitters, heaters, and the computers that keep the whole spacecraft oriented. The engineers who build them know the output will fade following a fixed physical decay curve nobody can slow down. What they do not know is exactly how long the fading can be managed, or how creative the fixes will eventually need to be, decades after every original designer has retired or died. Attached to the spacecraft's side is a record gold-plated copper, 12 inches across, sealed in an aluminum jacket, etched with symbolic instructions for playback. A diagram of the hydrogen atom used as a universal unit of time and measurement, and a map of pulsars pointing back toward the sun, in case anything that finds it needs to know where it came from. It carries greetings in 55 languages, natural sounds of Earth, whale calls, thunder, laughter, and 90 minutes of music chosen to represent the whole of human culture in a single disc, from Bach to Chuck Berry, to traditional recordings from cultures with no other record in the archive of Western science. Carl Sagan leads the committee that assembles it, working against a deadline of weeks, not years. The record is not built for scientists, it is built for whoever or whatever might find it, millions of years from now, long after Earth and everyone on it are gone. It is bolted to a spacecraft that is not expected to survive the decade. It will in fact outlive the Sun. The first stop is Jupiter. Voyager 1 arrives in March 1979, after a year and a half of flight, closing the distance at a pace no crewed spacecraft has matched before or since. Its cameras find something nobody predicted, an active volcano erupting on the moon Io caught mid-plume against the black of space. It is the first time a volcanic eruption is photographed anywhere beyond Earth. The discovery reshapes what scientists thought they knew about small, cold-seeming moons. Io is neither small in consequence nor cold in truth. Tidal forces from Jupiter's enormous gravity flex the moon's interior constantly, generating heat through friction alone, and Voyager 1 finds this out by accident. On the way to somewhere else, its cameras also return the first close images of Europa's cracked icy surface, a moon scientists will not seriously consider as a candidate for hidden oceans until decades later, and detailed views of Ganymede and Callisto, moons larger than Mercury that had, until this flyby, been little more than points of light in even the best Earth-based telescopes. Voyager 1's instruments also confirm for the first time that Jupiter has a ring system of its own, faint and dusty compared to Saturn's invisible from Earth, found only because the spacecraft finally flew close enough to look. The flyby lasts only a matter of days out of a year and a half of travel, but it returns more new information about the Jupiter system than the previous 3 centuries of telescope observation combined. Then comes Saturn. The spacecraft reaches the ringed planet in November 1980. Its cameras resolve detail in the rings that no telescope on Earth has managed. Thousands of individual ringlets, braided structures, gaps carved by unseen moons spoke like features that seem to rotate with the planet's magnetic field rather than its orbital motion. A puzzle that takes scientists years to explain. Then comes a single, deliberate choice that will define everything after. Mission planners aim Voyager 1 close past Titan, Saturn's largest moon, a world wrapped in a thick orange haze that hides its surface completely. The flyby returns almost no images of the ground below the clouds, but it accomplishes something more important to the people who design the trajectory. The gravity of Titan bends Voyager 1's path sharply upward, out of the plane where the planets orbit, and out of any future chance to visit Uranus or Neptune. It is a trade the mission team makes on purpose. They already have a second spacecraft, Voyager 2, still down in the plane of the planets, still able to reach the outer worlds years later. Voyager 1 is sent on a different errand, straight out as fast as physics will allow toward the edge of everything the sun can reach. For the next decade, Voyager 1 does not visit another planet. It travels. Along the way, its instruments continue to sample the solar wind, the interplanetary magnetic field, and the faint background of cosmic rays leaking in from beyond the solar system, building a data set that stretches unbroken across more distance than any instrument had ever covered before. In February 1990, at Sagan's urging and over some internal resistance from engineers worried about pointing a fragile, aging camera system directly at the sun, the mission team turns the spacecraft's camera around, back toward the inner solar system, and takes one last photograph before the imaging system is shut down for good. In the frame, Earth appears as a single point of light, less than a pixel wide, suspended in a band of scattered sunlight. One of 60 images that together make up what becomes known as the family portrait, the first photograph of the solar system taken from outside it. Sagan later calls the Earth frame the pale blue dot. It becomes one of the most reproduced photographs ever taken, not because of what it shows, but because of what it does not. No borders, no cities, no evidence that anything happening on that speck has ever mattered to the universe around it. After that frame, the cameras go dark. They are never turned on again. Every image Voyager 1 will ever return to Earth has already been taken. And every one from this point forward will be data, not pictures. Around this same period, NASA formally renames the ongoing mission the Voyager Interstellar mission, an acknowledgement that both spacecraft have already outlived their planetary objectives and are now officially headed somewhere no mission had been designed to study before. The boundary of the sun's influence itself and whatever lies beyond it. Through the 1990s, the spacecraft keeps moving outward, and the mission team keeps managing a budget that only shrinks both in electrical watts and in the funding allocated by an agency with newer, flashier missions competing for the same money. 4 watts of power vanish every year, a slow bleed with no way to stop it. Engineers begin switching off instruments and heaters that are not essential to keep the spacecraft alive, prioritizing the systems that let it navigate, transmit, and still do useful science on the way out. The plasma spectrometer, one of the original 11 instruments, eventually stops responding reliably and is left off rather than risk damaging other systems trying to revive it. Each shutdown is a one-way decision. Once a heater is off, the components it protects are exposed to cold that can crack solder joints and kill a system permanently. There is no repair crew, there is no second chance. Every choice has to be right the first time, made by people who will not be at the agency in some cases by the time the consequences arrive. On Earth, keeping in touch with a spacecraft this far away requires antennas built for exactly this kind of distance. NASA's Deep Space Network, a set of giant dish antennas in California, Spain, and Australia, positioned roughly a third of the way around the globe from each other, so that as Earth rotates, at least one dish always has a clear line of sight to the spacecraft. The signal Voyager 1 sends home arrives at a strength so faint that the network's receivers are by some engineer's description, listening for a whisper fainter than a digital watch battery, spread across a distance measured in billions of miles. Every bit of data has to be extracted from noise using error correction schemes, designed decades ago and refined since, because there is no way to ask the spacecraft to simply repeat a message more loudly. It only has so many watts to spend on its transmitter, and every one of them has already been accounted for. In 2004, Voyager 1 crosses the termination shock, the point where the solar wind, the stream of charged particles blown outward by the sun, slows abruptly as it runs into the thin gas of interstellar space. It is the first sign that the spacecraft is nearing the true edge of the sun's domain. The instruments that detect it are, at this point, over a quarter-century old, running on power far below what they were designed for, and still returning clean data. Nobody who built them in the 1970s used components meant to survive this long. They survive anyway. Then on August 25th, 2012, though it takes months of data analysis to confirm the exact date, Voyager 1 crosses the Heliopause. This is the true boundary of the sun's bubble, the heliosphere, the place where the solar wind finally gives way entirely to the material drifting between stars. In an instant, by the standards of a journey this long, the density of charged particles around the spacecraft jumps by a factor of 40. The magnetic field direction barely shifts, which puzzles scientists for years, since a clean boundary was expected to bend the field more sharply. And some models have to be revised to account for a boundary that is more permeable and less like a wall than anyone had assumed. Voyager 1 becomes the first human-made object to leave the heliosphere and enter interstellar space, a fact NASA does not announce publicly until September 2013, once the plasma data confirms what the particle counts had already suggested. It is 35 years and 20 days since launch. The spacecraft that was built for a 4-year mission to 2 planets is now further from home than any object humans have ever sent, and still transmitting. Interstellar space is not empty, it is simply thin and cold and shaped by forces the inner solar system never has to contend with. Voyager 1's remaining instruments, the magnetometer, the plasma wave subsystem, the cosmic ray detector, the low-energy charged particle instrument, begin returning the first direct measurements of this environment ever recorded. They find that the interstellar magnetic field is stronger than models predicted, and oriented at a slight angle to the heliosphere's own field rather than perfectly aligned, a detail that reshapes theories about how the two regions interact at their border. They find turbulence, plasma waves triggered by outbursts from the sun that take over a year to reach the spacecraft and register as ripples in the surrounding interstellar gas. Structure in a region scientists had mostly modeled from a distance, never sampled directly. Every additional year the spacecraft survives is a year of data. No other instrument, anywhere, is capable of collecting, because no other spacecraft has gone this far, and none currently in flight is built to last long enough to catch up. Voyager 2 will follow its sibling across the same boundary in November 2018, 6 years later, on a different heading, giving scientists 2 independent samples of the same edge, taken from 2 different directions. But survival for a spacecraft built in the 1970s and running for decades past its design life is not passive. It is a fight the ground team wages continuously in small decisions, most of which the public never hears about. In 2017, engineers discover that the primary thrusters used to keep Voyager 1's antenna pointed at Earth are degrading, their tiny fuel channels clogging with residue after decades of use, each pulse of hydrazine propellant leaving behind a little more build-up than the last until the thrusters can no longer fire cleanly enough to trust. The solution is to reactivate a set of backup thrusters that had not been fired since 1980. 37 years earlier, thrusters nobody expected to need again, originally intended only for the planetary flybys that ended decades before. Engineers dig through paper records and old software documentation, some of it written in programming languages few active engineers still use daily, to figure out how to safely switch control over without losing the spacecraft's orientation in the process. It works. The antenna stays pointed at Earth. It is the kind of fix that only works because a handful of engineers still remember, or can still find the paperwork for, hardware from a program most of their colleagues consider ancient history. By the early 2020s, the spacecraft's power budget is thinner than it has ever been, and the list of instruments still drawing current is shorter than the list that has already gone dark. Then, in November 2023, something worse than a scheduled shutdown happens. Voyager 1 stops sending readable data. Its radio signal is still arriving at NASA's Deep Space Network on schedule, proof the spacecraft is alive and still transmitting. But the content of the signal is garbled, a repeating pattern with no discernible structure. Nothing the ground team's software can pass into telemetry or science. For a spacecraft 15 billion miles away, with a one-way signal delay of over 22 hours, this is close to the worst kind of failure. Engineers cannot see the problem directly. They can only send a command and wait 2 full days for any hint of a response, one experiment at a time, with no guarantee any single attempt will reveal anything useful. The investigation stretches on for months. Engineers work from a functioning replica of Voyager 1's onboard systems, built decades earlier and kept in storage largely for exactly this kind of emergency, testing potential fixes on Earth before ever risking a command to the real spacecraft. Eventually, the team traces the fault to a single corrupted chip inside the flight data subsystem, the onboard computer responsible for packaging science and engineering data before it is transmitted home. The chip has failed after decades of operation, and with it, roughly 3% of the subsystem's memory becomes unusable. Memory that happens to include a portion of the code needed to format outgoing data correctly. There is no way to replace the chip. There is no way to send a technician. The only tool available is software written and tested on Earth using that decades-old engineering replica, then transmitted across 15 billion miles and 2-day round trips. One careful step at a time, each command a small bet that the spacecraft will interpret it exactly as intended, with no chance to correct a mistake for another 2 days. In April 2024, after 5 months of silence in any meaningful sense, engineers successfully relocate the affected code to a working section of memory. Voyager 1 begins returning readable engineering data again. Months later, its science instruments resume transmitting as well. The spacecraft that some engineers had quietly begun to write off is talking again. Its first coherent words in almost half a year arriving as ordinary telemetry, numbers in a data stream, nothing dramatic to look at, and everything to the people who had spent 5 months not knowing if they would ever hear from it again. The fix does not undo the underlying problem, only roots around it, and it does not stop the 4 watts a year still draining from the generators. Through 2025 and into 2026, the shutdown list grows longer. The cosmic ray subsystem, one of the instruments that helped confirm the Heliopause crossing in 2012, is switched off in February 2025 to conserve power for systems the team judges more essential to keeping the spacecraft alive. The low-energy charged particle instrument follows in April 2026. By that point, only 2 of Voyager 1's original 11 instruments are still returning data, the magnetometer and the plasma wave subsystem. The same tool that first confirmed the density jump marking interstellar space back in 2012. Voyager 2, its twin still trailing behind on a separate exit path from the solar system, has 3 instruments left running, a small, quiet distinction between siblings that left Earth 16 days apart in 1977 and have not been in the same place since. In April 2026, engineers shut off yet another system, this time in the hope of buying enough power margin to attempt something the team has nicknamed, informally, the Big Bang. A planned software and power reconfiguration meant to stretch the mission further, and, if it succeeds, possibly bring a dormant instrument back online, rather than only losing more. It is a gamble built entirely on the idea that a 50-year-old spacecraft can still be reasoned with from a distance if the people doing the reasoning are patient enough and willing to risk a command that could just as easily end the mission early as extend it. And still it keeps moving outward at roughly 38,000 miles an hour, adding more than 3.5 astronomical units to its distance from the Sun every single year. By the middle of 2026, Voyager 1 sits more than 15 billion miles from Earth, a distance so large that a radio command leaving Earth's antennas takes nearly 23 hours just to arrive. On November 13th, 2026, by NASA's own projection, Voyager 1 will cross a threshold no human-made object has ever reached. One light day from home. At that distance, a signal traveling at the absolute speed limit of the universe needs a full 24 hours to arrive, and a reply needs another 24 to come back. Susie Dodd, the mission's project manager, has described what that means in the plainest terms she can offer. Say good morning to Voyager on a Monday, and the answer comes back Wednesday. Not because the spacecraft is slow to respond, because the distance itself has become the obstacle, measured now not in miles but in the length of a day and a night, twice over, just to complete one sentence of conversation. Nothing else humans have built has ever forced that kind of patience. Every prior record for distance, held first by Pioneer 10 and then surpassed by Voyager 1 itself, back in February 1998, was a matter of miles and years. This one is a matter of days spent waiting for a single reply, a scale of delay that turns even routine engineering checks into something closer to correspondence with a very slow, very distant relative who is, against every reasonable expectation, still writing back. NASA's own engineers, working from the best current estimates of the remaining power curve, believe Voyager 1 can keep at least one instrument alive into the early 2030s. If nothing else fails first, and if the team keeps finding fixes as inventive as the ones that have carried it this far. That target puts the mission on track to reach its 50th anniversary in September 2027. A date the current team has explicitly named as a goal, not just a milestone, since every year past it now depends on decisions being made in real time, not on any plan drawn up in the 1970s. After that, the math stops bending. The plutonium will keep decaying at its fixed, unhurried rate, regardless of what anyone on Earth wants from it, and at some point there will not be enough electricity left to power a transmitter, let alone an instrument. The spacecraft will not explode or break apart or announce its own end. It will simply stop answering on some ordinary day, mid-conversation, the way it briefly did in November 2023, except this time with no fix waiting on the other end of a 2-day round trip. When that happens, Voyager 1 will not stop moving. It will keep traveling outward, silent, carrying its gold record past stars that do not yet have names assigned by anyone alive today. Current estimates put it on a course that will bring it, in roughly 40,000 years, into the loose neighborhood of a star in the constellation Camelopardalis. Not a close encounter by any human measure, but the nearest thing to a destination the spacecraft will ever have again, long after the last engineer who worked on its 2023 recovery has died, long after the equipment used to build its replica on Earth is retired and forgotten, long after every language spoken into its golden record has changed beyond recognition or vanished outright. Voyager 1 will still be out there, cold, dark, and utterly quiet, carrying 90 minutes of music that no living thing has any way of playing. The silence when it finally comes will not be a malfunction. It will be a schedule kept exactly on time 50-some years after a rocket left Florida carrying a spacecraft nobody expected to still be listening. The record itself deserves more time than a single paragraph gives it, because almost nothing about how it was made was ordinary. In the summer of 1977, with the spacecraft already built and the launch date fixed, Carl Sagan is asked by NASA to assemble something no prior mission had ever carried. A message meant not for scientists on Earth, but for whoever might find the spacecraft after everyone alive that year is gone. He has roughly 6 weeks to do it. He pulls together a small team, among them the astronomer Frank Drake, who works out how to encode images as analog signals that a sufficiently advanced finder could, in principle, decode without any instructions in a shared language. And the writer Anne Druyan, who joins the project as creative director, and partway through the process has her own brainwaves recorded as one of the disk's stranger contributions, an EEG session intended to capture, in electrical form, the pattern of a human mind in the act of thinking about the record itself. She and Sagan fall in love during the project and marry not long after. The record's cover carries no photograph and no drawing of a person. Instead, it is etched with instructions meant to be readable through physics rather than language. A diagram showing how to build a playback device and spin it at the correct speed, a symbol representing the fundamental transition of a hydrogen atom used as a universal unit of time, and a map of 14 pulsars, each with a precisely marked period, positioned relative to the Sun in a way that would let a technologically capable finder calculate, decades or millennia later, exactly when and from where the spacecraft was launched. It is the same kind of pulsar map used on the Pioneer plaques a few years earlier, refined for a mission the Pioneer team never had the payload budget to attempt. Inside the finished archive are 116 images encoded in analog form, showing scenes chosen to represent life and knowledge on Earth. Anatomy, agriculture, cities, mathematics, a diagram of DNA, a photograph of a supermarket, children, a woman breastfeeding, an image of a page from a physics book. There are spoken greetings in 55 languages, some ancient, some spoken by only a handful of people even in 1977. A scattering of natural sounds, wind, surf, thunder, birdsong, whale calls, and the sound, deliberately included, of a mother's first words spoken to a newborn child. 90 minutes of music close out the disc, chosen to span cultures and centuries rather than favour any single tradition. A Bach Brandenburg concerto, a Beethoven string quartet, Chuck Berry's Johnny B. Good, a Peruvian panpipe ensemble, a Navajo night chant, a Georgian folk chorus, an Azerbaijani bagpipe tune, an Indian raga, and dozens more assembled by a committee racing a launch date that would not move for anyone's convenience. When Saturday Night Live jokes, not long after launch, that the only reply humanity has received from an alien civilization is the message, "Send more Chuck Berry," it becomes one of the record's more famous footnotes, a joke that only works because the record itself had already become, within weeks of its launch, a piece of cultural shorthand. None of it was made to be played by anyone at NASA. Once bolted to the spacecraft, the record leaves Earth for good. There is no copy in orbit, no backup meant for public listening, only occasional replicas built afterward for museums and archives. The original travels with Voyager 1, permanently, whatever the spacecraft's fate. The trajectory that made all of this possible was not something engineers invented for the Voyager program. It was something one graduate student noticed almost a decade earlier. In 1965, a young engineer at the Jet Propulsion Laboratory named Gary Flandreau, working on his own initiative rather than as an assigned project, calculated that Jupiter, Saturn, Uranus and Neptune would align in the late 1970s in a configuration that occurs only once every 175 years. A geometry that would let a single spacecraft use each planet's gravity to bend and accelerate its path toward the next, reaching all 4 outer planets on one mission using only a fraction of the propellant a direct flight to each would otherwise require. Flandreau's memo becomes the seed of what NASA initially studies as the Grand Tour program, an ambitious plan for 4 separate spacecraft, each built for the punishing radiation and distance of the outer solar system, launched in pairs to cover different combinations of planets. Budget realities in Washington in the early 1970s cut that plan down considerably. Congress and NASA leadership balk at the cost of 4 purpose-built outer planet spacecraft, and the Grand Tour program, as originally conceived, is cancelled. What survives, reshaped and renamed, is a more modest pair of spacecraft, adapted from the design used for earlier Mariner missions to the inner planets, tasked officially with visiting only Jupiter and Saturn, though built with enough redundancy and instrument flexibility that an extended mission to Uranus and Neptune remains at least theoretically possible. if the first two flybys go well and the hardware holds up. That modest pair becomes Voyager 1 and Voyager 2. The rare alignment Flandreau calculated does not repeat until the next century. If the missions had slipped past their launch window in 1977, no spacecraft alive today would have had the same opportunity to reach all 4 planets on a single trip. It falls to Voyager 2 to actually complete the tour Flandreau first described. Voyager 2 launches on August 20th, 1977, 16 days before its twin, but on a slower, more curving trajectory designed from the outset to preserve the option of continuing on to Uranus and Neptune, a path Voyager 1's faster, more direct route to Jupiter and Saturn could never have supported. The two spacecraft, identical in design, diverge almost immediately into 2 different missions that happen to share a name and a launch year. Voyager 2 reaches Jupiter in July 1979, 4 months after Voyager 1, and uses the second pass to fill in gaps the first flyby's cameras had missed, catching further detail on Io's volcanic activity and returning the first clear evidence that the moon Europa's icy crust is crossed by a network of long, straight fractures, a detail that decades later becomes central to the case for a liquid ocean hidden beneath that ice. At Saturn in August 1981, Voyager 2's trajectory is deliberately kept clear of Titan, since Voyager 1 has already used its one shot at that moon to bend its own path out of the solar system. Voyager 2 continues instead directly on toward the 2 planets no spacecraft from Earth has ever approached before. In January 1986, after 4.5 more years of flight, Voyager 2 reaches Uranus, remaining to this day the only spacecraft ever to visit that planet. It discovers 10 previously unknown moons, maps, a magnetic field tilted at an almost sideways angle relative to the planet's spin axis, a puzzle nobody had predicted, and returns close images of Miranda, a small moon whose surface shows canyons and cliffs so extreme and disordered that some scientists initially describe it as looking as though the moon had been shattered and reassembled. 3.5 years later, in August 1989, Voyager 2 completes what Flandreau's 1965 memo had first made possible: a flyby of Neptune, the only one any spacecraft has ever conducted. It finds a colossal storm system nicknamed the Great Dark Spot, winds faster than anywhere else recorded in the solar system, and discovers active geysers erupting from the icy surface of Neptune's largest moon, Triton, one of the coldest and most distant objects ever imaged in detail by a human-built camera. With Neptune behind it, Voyager 2's cameras are switched off, following the same fate as its twins had years earlier, and the spacecraft turns fully toward the same kind of interstellar mission Voyager 1 had already begun. It crosses the termination shock in 2007, 3 years after Voyager 1 did, on its own separate heading, and crosses the Heliopause into true interstellar space on November 5, 2018, 6 years after its twin, giving scientists a second independently measured crossing point on the opposite side of the solar system's bubble. The 2 spacecraft, launched 16 days apart from the same Florida coastline, have not been anywhere near each other since 1977, and by the 2020s are moving apart from Earth in almost entirely different directions, each one a lone, independent witness to a boundary that no human eye will ever see directly. None of this data from either spacecraft would reach Earth at all without the network built specifically to catch it. NASA's Deep Space Network consists of 3 ground stations, spaced roughly 120 degrees apart in longitude, one at Goldstone in the California desert, one near Madrid, Spain, and one near Canberra, Australia. The spacing is deliberate and load-bearing to the entire mission. As Earth rotates, any single antenna eventually turns away from a distant spacecraft and loses its line of sight. With 3 stations spread evenly around the globe, at least one of them can always see Voyager 1 or Voyager 2 at any hour on any day without a gap. It is a system built to guarantee that a signal traveling for hours or eventually for a full day across space is never simply missed because the wrong side of Earth happened to be facing the wrong way when it arrived. Each complex operates giant parabolic dish antennas the largest of them 70 meters across, roughly the length of a football field, engineered specifically because a spacecraft transmitting from billions of miles away cannot spare the power for a loud signal. By the time a transmission from Voyager 1 reaches one of these dishes, its strength has fallen to a level engineers routinely describe as a small fraction of the power in a digital wristwatch battery, spread out and weakened across a distance so vast that the signal arrives, not as a clear broadcast, but as something closer to a whisper, the size of Earth's entire radio noise floor, buried and waiting to be extracted. The dishes compensate through sheer collecting area, through supercooled receivers designed to minimize their own electronic noise, and through error-correcting codes built into the data itself, mathematical redundancy that lets ground computers reconstruct a clean signal even from a transmission that arrives partially degraded. None of this technology existed in its current form when Voyager 1 launched. The network has been rebuilt and upgraded around the spacecraft for decades, a moving target of engineering improvements, chasing a signal that keeps getting fainter every year. If only because the distance keeps growing and the spacecraft's own transmitter keeps losing power right alongside everything else on board. Commanding either spacecraft is not a matter of typing an instruction and watching it execute. Every command aimed at Voyager 1 has to travel through the same physical limit as the data coming back. Nothing moves faster than light, and nothing about billions of miles of empty space can be shortened by better hardware on either end. In the spacecraft's early years, that delay was a matter of an hour or so each way. By 2026, it stretches close to a full day. Engineers plan every command sequence with this delay built in from the start, testing procedures exhaustively on the ground replica before ever transmitting them for real, because a mistake sent across a day-long gap cannot be caught and corrected in any hurry. It can only be waited out, and then, if necessary, corrected with a second command and another day's wait to see whether that one landed properly either. Voyager 1's climb to the edge of the solar system did not happen in silence, at least not in the sense of public attention. On February 17, 1998, at a specific moment engineers can pinpoint from tracking data alone, Voyager 1 passes Pioneer 10. The earlier NASA probe launched in 1972 and becomes the most distant human-made object from the Sun, a record it has held every day since. Pioneer 10 had a 6-year head start, but it also had a much slower final trajectory, having spent its own gravity assists on a more modest path. Voyager 1's faster route through Jupiter, chosen originally so it could scout ahead of its twin, ends up paying off in an entirely different way 16 years later, when it quietly overtakes a spacecraft that had already been coasting through the outer dark for a generation. There is no dramatic flyby to mark the moment, no image taken, no crowd watching a screen. It is simply a line crossed in the tracking logs, confirmed after the fact, a record that will not be threatened again until a spacecraft faster and further reaching than either Voyager is eventually built and launched, which, as of the mid-2020s, no funded mission yet plans to be. The program that produced both spacecraft was itself a scaled-down survivor of something far larger and never built. When Gary Flandreau's 1965 memo on the rare planetary alignment reaches NASA leadership, the agency's engineers first study a far more ambitious response, a program that would eventually be called the Grand Tour, built around new, purpose-designed spacecraft known internally as TOPS, short for Thermoelectric Outer Planet Spacecraft, machines conceived from the ground up to survive a decade or more of flight through the punishing radiation belts of Jupiter and the extreme cold beyond Saturn. The plan calls for as many as 4 separate TOPS spacecraft launched in pairs covering different combinations of the 4 outer planets, an effort large enough to require its own dedicated funding line and years of specialized engineering. Congress does not fund it. By 1972, facing budget pressure and competing priorities inside NASA itself, including the tail end of the Apollo program and the earliest planning for the Space Shuttle, the Grand Tour program as originally conceived is cancelled outright. What emerges instead, approved on a far smaller budget, is a project first named Mariner Jupiter Saturn 1977. built by adapting the hardware and instrument heritage of the earlier Mariner missions to the inner planets, rather than designing an entirely new spacecraft family from scratch. It is officially tasked only with visiting Jupiter and Saturn, a far more modest mandate than the 4-planet Grand Tour it replaces. Only later, once the design proves itself capable and hardy enough to plausibly survive further, is the mission renamed Voyager, and only after Voyager 1's success at Saturn does NASA formally commit Voyager 2 to continue on toward Uranus and Neptune, quietly completing, with one surviving spacecraft, the 4-planet tour that an entire cancelled program of purpose-built machines was once meant to accomplish. Almost none of the public excitement generated by the eventual Grand Tour, the pale blue dot photograph, the interstellar crossings, the 50th anniversary headlines would exist under the name or the budget originally proposed. It exists because a smaller, cheaper, repurposed pair of spacecraft was asked to do a bigger job than it was designed for, and did it anyway. Commanding either spacecraft is not a matter of typing an instruction and watching it execute. Every command aimed at Voyager, one has to travel through the same physical limit as the data coming back. Nothing moves faster than light, and nothing about billions of miles of empty space can be shortened by better hardware on either end. In the spacecraft's early years, that delay was a matter of an hour or so each way. By 2026, it stretches close to a full day. Engineers plan every command sequence with this delay built in from the start, testing procedures exhaustively on the ground replica before ever transmitting them for real, because a mistake sent across a day-long gap cannot be caught and corrected in any hurry. It can only be waited out, and then, if necessary, corrected with a second command, and another day's wait to see whether that one landed properly either. Voyager 1's climb to the edge of the solar system did not happen in silence, at least not in the sense of public attention. On February 17, 1998, at a specific moment engineers can pinpoint from tracking data alone, Voyager 1 passes Pioneer 10, the earlier NASA probe launched in 1972, and becomes the most distant human-made object from the Sun, a record it has held every day since. Pioneer 10 had a 6-year head start, but it also had a much slower final trajectory, having spent its own gravity assists on a more modest path. Voyager 1's faster route through Jupiter, chosen originally so it could scout ahead of its twin, ends up paying off in an entirely different way 16 years later, when it quietly overtakes a spacecraft that had already been coasting through the outer dark for a generation. There is no dramatic flyby to mark the moment, no image taken, no crowd watching a screen. It is simply a line crossed in the tracking logs, confirmed after the fact, a record that will not be threatened again until a spacecraft faster and further reaching than either Voyager is eventually built and launched, which, as of the mid-2020s, no funded mission yet plans to be. The program that produced both spacecraft was itself a scaled-down survivor of something far larger and never built. When Gary Flandreau's 1965 memo on the rare planetary alignment reaches NASA leadership, the agency's engineers first study a far more ambitious response, a program that would eventually be called the Grand Tour, built around new purpose-designed spacecraft, known internally as TOPS, short for Thermoelectric Outer Planet Spacecraft. Machines conceived from the ground up to survive a decade or more of flight through the punishing radiation belts of Jupiter and the extreme cold beyond Saturn. The plan calls for as many as 4 separate TOPS spacecraft, launched in pairs covering different combinations of the 4 outer planets, an effort large enough to require its own dedicated funding line and years of specialized engineering. Congress does not fund it. By 1972, facing budget pressure and competing priorities inside NASA itself, including the tail end of the Apollo program and the earliest planning for the Space Shuttle, the Grand Tour program, as originally conceived, is cancelled outright. What emerges instead, approved on a far smaller budget, is a project first named Mariner Jupiter-Saturn, 1977, built by adapting the hardware and instrument heritage of the earlier Mariner missions to the inner planets, rather than designing an entirely new spacecraft family from scratch. It is officially tasked only with visiting Jupiter and Saturn, a far more modest mandate than the four-planet Grand Tour it replaces. Only later, once the design proves itself capable and hardy enough to plausibly survive further, is the mission renamed Voyager. And only after Voyager 1's success at Saturn does NASA formally commit Voyager 2 to continue on toward Uranus and Neptune, quietly completing, with one surviving spacecraft, the four-planet tour that an entire cancelled program of purpose-built machines was once meant to accomplish. Almost none of the public excitement generated by the eventual Grand Tour, the pale blue dot photograph, the interstellar crossings, the 50th anniversary headlines, would exist under the name or the budget originally proposed. It exists because a smaller, cheaper, repurposed pair of spacecraft was asked to do a bigger job than it was designed for, and did it anyway. Titan, the moon Voyager 1 used to bend itself out of the solar system in November 1980, remained a haze-covered mystery for another 24 years after that flyby. Voyager 1's cameras, and later Voyager 2's from a more distant past, could not see through the moon's thick orange atmosphere to any surface detail at all. What finally answers the question of what lies beneath is not a Voyager spacecraft, but Cassini, launched in 1997 and arriving at Saturn in 2004, carrying with it a small European-built probe named Huygens, designed specifically to descend through Titan's atmosphere and land, or attempt to land, on whatever surface waited below. On January 14, 2005, Huygens separates from Cassini and drops through Titan's haze, becoming the first spacecraft ever to land on a moon in the outer solar system. It survives the descent and continues transmitting data from the surface itself for well over an hour, far longer than its minimum design requirement, returning images of a landscape scientists had only been able to guess at since Voyager 1's flyby, a quarter-century earlier. A shoreline of sorts, rounded pebbles that appear shaped by the flow of liquid, and evidence confirmed by later Cassini orbital passes of methane lakes and seas near the moon's poles. A body with weather, rainfall, and river channels running not on water, but on hydrocarbons cold enough to remain liquid only because Titan itself sits so far from the sun's warmth. It is, in a sense, the answer Voyager 1 never got to see, arriving decades later. Delivered by a mission that only became possible because Voyager's own flyby had proven Titan interesting enough to justify the trip. The golden record itself, sealed onto the sides of both Voyager spacecraft and now scattered across two different headings out of the solar system, was never meant to be heard by anyone still living on Earth. For decades, that meant the actual content of the record, beyond a handful of frequently reproduced photographs, remained something most people only knew about secondhand, through books and documentaries describing what it contained, rather than letting anyone actually listen to it. That changed in 2016 when a small independent record label, working with the same NASA archives and some of the same technical files used to build the original disc, produces a limited vinyl reissue of the complete golden record, remastered from the best surviving source material, packaged as a box set with the same cover diagrams etched this time onto the sleeve rather than a spacecraft. The project is funded through a public crowdfunding campaign that raises far more than its original target within days. Evidence of an appetite, still very much alive nearly 40 years after launch, to hear the exact 90 minutes of music and greetings that only two physical copies in existence, both currently in interstellar space, actually carry as originally intended. Museums and archives, including the Library of Congress, have since acquired copies of both the reissue and earlier partial replicas for public listening and display. The closest anyone on Earth will likely ever come to experiencing the record the way its makers intended, short of building a spacecraft capable of catching up to either Voyager and playing the original. Every one of these threads, the record's eventual reissue, Titan's answer arriving by way of Cassini and Huygens, The record distance milestone quietly passed in 1998. The Grand Tour program that never was circles back to the same fact. Voyager 1 was assembled from a smaller, cheaper plan than the one first proposed, launched on a schedule dictated by a planetary alignment that will not repeat for another century and a half, and sent outward carrying a message built in 6 weeks by people who knew they would never learn whether it was ever received. Everything that happened afterward, the volcano on Io, the pale blue dot, the crossing into interstellar space, the chip failure and its recovery, the light day milestone, still ahead in November 2026, was extra. The mission's real requirement was met at Saturn in 1980. Everything since has simply been the spacecraft continuing to answer for as long as anyone on Earth keeps asking. The dishes that make any of this communication possible were not originally built with Voyager's full journey in mind, and the story of the antennas is its own kind of quiet engineering drama. When NASA's Deep Space Network is first designed, its largest dishes measure 64 meters across, already enormous by any standard. Built through the 1960s primarily to support the Apollo program and the early planetary missions to Mars and Venus. As Voyager 2 approaches Neptune in the late 1980s, engineers realize the existing network, however large, will not be sensitive enough to pull a usable signal from a spacecraft that far away, transmitting at ever lower power as its own generators fade. Rather than build an entirely new facility, NASA extends the existing 64-meter dishes at Goldstone, Madrid and Canberra outward to 70 meters, adding new panels around the rims of dishes that were already, at the time, among the largest steerable antennas on Earth. The upgrade is timed specifically to be ready before the 1989 Neptune flyby, a deadline the network's engineers meet with almost no margin to spare. Every image and measurement Voyager 2 returns from Neptune, the Great Dark Spot, the geysers on Triton, passes through antennas that exist in their final form, only because one aging spacecraft's faint signal demanded it. Those same extended dishes go on to serve far more than Voyager alone. Once enlarged for Neptune, the 70-meter antennas become the backbone of NASA's communication with nearly every deep space mission that follows. The Mars rovers, the outer planet orbiters, the New Horizons mission to Pluto, all of them relying on infrastructure originally justified, funded, and rushed to completion because 2 spacecraft launched in 1977 needed somewhere sensitive enough to be heard. Voyager 1, in a real sense, built part of the ears NASA still uses to listen to everything else in the solar system. The decision to turn Voyager 1's cameras around for the pale blue dot photograph in February 1990 was not the uncomplicated sentimental choice it is often remembered as. Inside NASA, the idea meets real resistance before it is approved. Some engineers on the imaging team argue against it directly, worried that pointing the camera anywhere near the sun's direction, even with Earth appearing as nothing more than a faint point from that distance, risks damaging the Vidicon imaging system through stray light exposure, a system already well past its expected working life and with no way to repair it if something goes wrong. Others question the scientific value of the exercise altogether, since the image will show Earth as barely more than a single pixel, containing essentially no information a planetary scientist could use. Carl Sagan, who has been advocating for exactly this photograph since the mission's earlier planetary encounters, argues the case is not really scientific at all, but something closer to philosophical, a chance to let Earth see itself from a distance no camera will ever occupy again once the imaging system shuts down for good. Only after Voyager 1 completes its main imaging objectives at Saturn, with nothing left on the required list that the cameras are still needed for, does mission management agree to spend the remaining camera time on Sagan's request. The full sequence, 60 frames making up what becomes known as the family portrait, is captured on February 14, 1990. The pale blue dot frame itself, showing Earth suspended in a scattered band of sunlight from the spacecraft's own optics, needs months of processing back on Earth before the image is clean enough to publish, and it is not until 1994, in a public lecture later adapted into a widely read book, that Sagan gives the photograph the words most people now associate with it, describing the image as a reminder of how alone and small everything ever recorded in human history looks from that distance. The cameras are switched off permanently not long after the sequence is captured, a decision made partly to save the small amount of remaining power they still draw, and partly because there is, by that point, genuinely nothing left within their reach worth photographing. The recovery from the November 2023 communication failure involved a level of technical improvisation that took months to become public in full detail. Once engineers at the Jet Propulsion Laboratory isolate the fault to a single failed chip inside the flight data subsystem, they face a problem with no precedent in the mission's prior history. The code responsible for formatting Voyager 1's outgoing data is partly stored in the section of memory that chip once supported, and that code cannot simply be deleted or ignored, since the spacecraft has no way to transmit anything coherent without it. The team's solution, worked out over weeks using an exact software and hardware replica of Voyager 1 kept on Earth specifically for testing scenarios too risky to attempt directly on the real spacecraft, is to split the affected code into smaller pieces and relocate those pieces into different areas of the subsystem's surviving memory, adjusting the code as needed so each piece still knows where to find the others once reassembled. Because the smallest error could risk losing the spacecraft's ability to communicate at all, permanently, engineers test the fix repeatedly on the ground before ever transmitting a single command toward the actual spacecraft, each real attempt separated from the last by roughly 45 hours, the full round trip required for a command to arrive, and a response, if any, to return. The first working piece of relocated code, covering the section responsible for engineering data alone, is transmitted in April 2024. When a readable signal returns days later, it is treated internally as confirmation that the fix works, though full science data does not resume until later in the year, once additional code sections are relocated using the same slow, careful method. The entire recovery, from first detecting garbled data to fully restored science transmission, spans very close to a full year, conducted entirely through radio commands sent across a gap of light and time that no engineer involved could shorten by so much as a second, no matter how urgent the work felt on the ground. Every one of these details, the antennas enlarged for a flyby and then repurposed for every mission after it, the internal argument over whether to risk the cameras at all, the painstaking relocation of code across a communication delay measured in days, describes the same underlying condition. Voyager 1 has never survived on the strength of its original 1977 engineering alone. It has survived because, every decade since, a new group of people on Earth has chosen to keep answering when it calls, often at real professional risk, often using tools and records inherited from engineers long retired, sometimes not sure until the moment to reply finally arrives, 1 or 2 days later whether the spacecraft heard them at all.